All right, guys, it is also being live streamed. I'll know at what location in a moment. All right. And so, for those of you who are interested in the uh, live stream version, am I doing this? What just happened? Today, no, hang on. Bear with me, guys. I'm just arranging the things here. I have no idea why it is coming out to be the wrong one. Give me one more second. Share. So, all right, guys, the link for that is on your Slack for those of you who would like to see it on the YouTube. And I'll get started now. So, the autoencoders. The basic architecture of the autoencoder is like this. It's like this. In your mind, we always think of autoencoders as like this. A symmetrical object, laterally symmetrical. This is the hidden representation. People often write it as H or Z or something like that. This is the latent space representation. And this is your input goes in, and X prime comes out. Actually, let me use capital X. Uh, X prime comes out. And the idea is that if you take a loss function, which is x minus x prime square, right, summed over all the I values, then, and you try to minimize the loss, then you have an autoencoder. The basic idea was that let this function be f such that f, the f takes you from x to the hidden representation. Let this, this is the encoder function. This is the decoder function. And G such that you go from a hidden representation back to X prime, right? So this is the reconstructed input. Reconstructed input. This is your basic autoencoder. Now, in this autoencoder, this entire thing, you may have just one hidden layer, which is the latent layer itself, but much more commonly, you have many more layers sitting here. And this side is literally the mirror opposite of that. Yeah. Now, the reason we keep more layers is the same reason we have many layers in a deep neural network. Namely, computations are much faster. It is more efficient. Right? The learning is quicker and better. So you have many more layers here in between. And we will see this in the lab today. So this is your vanilla autoencoder. The loss function, if you look carefully, it is very common sense thing. It is basically saying, what is the gap between the reconstructed input and the input? So this is the input. This is the output. And the output should be able to reconstruct the input, even though we have passed it through a bottleneck, right? There's a big bottleneck which comes out with a hidden representation of the input. So once you have trained it, then what happens is, so let's put it this way. This part is the encoding part, encoder part, and this part is the decoder part of the architecture. Are we together? Now, what do? Once the training is over, then what you can do is you can use the two pieces separately. For example, where am I? You could do things like while encoding the data. So suppose you're doing data compression or coming up with a hidden representation. You can just give X and H will be your output. Right? And then if you so choose, you can store this value. You can store it. So one example could be, you can, for example, compress images if you want through this process. Right? The other part is later on, when you want to do a decoding of it, what you would do is while decoding, you now use the other part of it, the decoder part of it. And remember, this was your F and this is your G. And what happens is X goes in and X prime comes out. A reconstructed input comes out. Right? And so one very simple use thing that you can think is, suppose you have a data whose representation is rather large. For example, a TIFF image or something like that. One thing you could do is you could pass it through an autoencoder, through an encoder, get the hidden representation, send the hidden representation over the wire, send it over the wire. Then at the other end, you can reconstruct the original image from this compressed representation. So you can use it for compression and transmission and so forth. That's a very basic thing. But there are other use cases that we learned about the autoencoders. For example, we learned that in the autoencoders are in some sense a generalization of principal component analysis, isn't it? In a principal component analysis, you look for a linear lower transformation to a lower dimensional space. The operative word is a linear transformation. Right? And we do our eigenvalue decomposition and so forth of the covariance matrix to get there. It turns out that autoencoder and the PCA are quite related. So let me put a sidebar of PCA versus autoencoder. If you do an autoencoder with only one hidden layer, the H itself, and nothing else, and you have X going in, and you take the sigmoid function, you take a unit activation function. In other words, you don't activate, you don't do any nonlinear transformation. So then what would happen is, once you have trained the data, you will find that your H is related to or equivalent to a PCA. It's not directly a PCA. It turns out that it's sort of a, you need a little bit more, but it is equivalent to a PCA. And that is something. So in some sense, you can think that the PCA is a generalization of your, autoencoders are a generalization of a PCA. But autoencoders are more than PCA. They have this ability to do a lot of things that you don't expect, for example, to be able to achieve through PCA and so forth. So one of the examples is we talked about is the denoising autoencoder. In the denoising autoencoder, what you do is the same autoencoder architecture. It doesn't change, but you add one extra layer. Let me just call it the noise injector. So you take X, it goes in. What comes out typically is represented as X tilde. It is the same input with noise now. So you introduce noise. The noise can be anything. It could be Gaussian noise, normal noise, sparkle noise, pick your noise and you can inject that. And then what you expect though, the loss function is not with respect to the x tilde, but it is with respect to x prime. Loss is still with respect to the original image or original data input. It need not be image, it could be anything, by the way. Right? So that it could do that. When you do this, what you do in effect is you create an autoencoder that cleans out noise. And it will clean out the noise from the image and so forth. And in today's lab, we will see how it is done. So here, what you're doing is you're sampling into a noise thing. And basically, this is, you can think of it, for those of you who are mathematically inclined, there is the relationship of this is essentially, roughly speaking, you take the input and then you apply, you do some additive noise. Some additive noise you get to come up with a distribution for this. Right? So now comes a third point I mentioned, which was the contracting um, autoencoder, which is very similar to the above, with the one exception that what it does is you don't inject noise, you pass in X, you have your FG. So it goes in through this. But what you do is, sorry, you play around with your loss function itself. In your loss function, what you do is x prime loss function will have the normal x minus x prime term, square term with the appropriate sigmas and so forth. But what you do is you actually add something very peculiar. You add a resistance to change. You say that the value, the hidden representation, h, how does it change with, let me just use some vector notation, gradient of h with respect to h, right? In simple terms, in one dimension, it is like the rate of change of hi with respect to any one of the input features xj, right? You try to minimize the change. It's very peculiar. You're trying to make the internal representation insensitive to changes in the input. You say that, well, one easy way to do that is just make it constant. If you do that, though, this term will blow up. This part of the loss term blows up. So this part, by the way, it is the Jacobian. So you add the Jacobian of that. So and forget about the. Let me just put it this way. So this part encourages x prime to, I mean, this part encourages x prime to be to tend to x. On the other hand, this part is interesting. If you want x prime to catch up to x, you would imagine that h itself would be sensitive to x, to the input. But that sensitivity, or rather oversensitivity, is not, it makes the autoencoders unstable. So what you do is you add a resistance term, you add a penalty to the sense. See, if you look at the derivative, what is the derivative? Derivative is a measure of sensitivity, right? So for example, if you have a curve like this, and this is x and that is y, at this point, you would imagine that y is very sensitive to values of x at this point, right? So a, whereas at b, y is not so sensitive to, at b, y is not so sensitive to x, right? The derivative is small. Whereas here, the rate of change is very high. Your small changes in x will lead to a big change in y. So it's very sensitive to the input, right? So that is what it is. Derivatives can also be thought of as measures of sensitivity. And what you're basically saying is, let's add a penalty term such that the 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 hidden representation, the latent representation, is not so sensitive to the input. Now that looks paradoxical. If it is not sensitive to the input, how in the world would you have this x prime close to x, right? And so that creates two competing forces. One part in this loss function says catch up to x, output must catch up to x. But for it to do that, obviously, it will try to make the h, the hidden representation, somewhat quite sensitive to input. And then there is a penalty factor that prevents it from being oversensitive to it. So what happens is with both the denoising autoencoder and the contractive version, by the way, this is the Jacobian term that penalizes oversensitivity. So I remember that I forgot to mention the contractive one in greater detail. So today, I hope I've done that. So if this math worries you, to ignore the math. Just think of it as intuitively that you have a penalty term for oversensitivity. So what it means, what both of these do effectively is, let us say that your data. See, when you have data, let's say that your data is, and I'm now going back to the picture that is there in the original research paper, and they literally draw a picture like this. They say that suppose this is your input manifold, right? And it has some hidden representation. What you want to make sure is, suppose this is one data point. Let's say if you're looking at MNEST, this is the letter 1 and this is the letter 2 and so forth, right? What you want to do is, suppose you get a perturbation of it, of the input. You get something like this, 1 prime. These autoencoders, the denoising and the contractive, their main goal is to be able to project it down to this underlying manifold and realize that 1 prime is actually 1. And so when it does the transformation into the H hidden representation, all these perturbations of 1, and let's say there's another perturbation here of 1 prime, double prime, right? All of these, let me mark the points with deeper color, 1, 2, and the point itself. What you want to make sure is that all three of these map to exactly the same point in the edge space. Are we together? So small perturbations of the input, your hidden representation stays insensitive to it, which is the value of a Jacobian term, or which is the value of in the direct denoising, inserting a noise, sample noise into the autoencoder. You prevent it from being unstable or being oversensitive to it, right? So that is the theory of autoencoders. Now you can build autoencoders in two ways. You can build autoencoders with feed forward network. You know, uh, you can put a feed forward or dense layers, or dense or linear or fully connected, fully connected. You can pick your synonym. You can use these to build layers, to build your autoencoder, or you could do other things. You could, for example, use convolutional layers. And one of the things I'll show you in the lab is it's the flexibility of it. So long as you stick to this basic architecture, something like this, uh, you have an autoencoder. By the way, here I create a bottleneck. Now, I did mention that you can have overcomplete networks also. You can have this also for a sparse representation, in which you, even though it looks lots of things, what you expect is for a given input, most of the hidden dimensions will be zero, right? You force most of these neurons to not fire and only some of them to fire. So that is the sparse auto encoder. And the literature of autoencoder is pretty vast and growing. You know, there's more and more work being done all the time with autoencoders because they are so useful. Okay. So in the lab today, we will do the autoencoder, the denoising autoencoder, the convolutional autoencoder, the denoising convolution autoencoder, and you will see that these are fairly simple beasts. You can easily code them up. Now, I have put the sample code on the web. I noticed that some of you had asked me a few days earlier to put the code. Unfortunately, as I mentioned, I was really taking a break and resting this particular weekend, so I didn't post it. I posted it now, so you can download it. So with those words, let me see if I can bring up the lab. Give me a moment. Any questions, guys? Oh, by the way, I didn't cover the variational autoencoder. Again, we won't do variational autoencoder now, autoencoder, because that's a separate topic. But the basic idea there was, again, it's a generative model. What you do is you have a hidden representation H, but the hidden representation is a parametrized representation. It is basically a Gaussian mixture, typically. If you think of it as Gaussian mixtures, then what happens is all you're caring about is the mu and sigma, the mean vector and the sigma vector, right? Or let me use the little sigma because you have only diagonal terms. So you make this part a bunch of mu's and this part a bunch of sigmas. Then there is a sample, you sample off this. And then when you train this autoencoder, what you can thereafter do is sample off this and produce your output. So that's the variational autoencoder. Now the theory was, if you recall, we talked about variational inference. It's a very a Bayesian argument. I won't repeat that today because we have a lab to do, but this is just sort of a background to that. So these were the autoencoders we covered. There are more. And on the website and a course page, I put a whole link to some way, the whole section for autoencoders, and you will see that their entire website's dedicated to the research on autoencoders. All the autoencoder work that is being done, emerging, and so on and so forth. So that is a huge deal. So with that, I will now go to the lab part. Let me bring my keyboard. It seems to not be liking it. 1 second. Give me a moment to attach a different keyboard. All right, with some luck, this works. Yes, it does work. So I'm opening. By the way, any questions, guys, on autoencoders? Did you feel that we understood autoencoders?
Sir, one question here.
Go ahead.
So the Jacobian is a constant, right, sir? Can you scroll up a little bit? I just wanted to check. Yeah, I think it's Jacobian is a constant kind of lambda, right? It has some values. Right?
No.
Or the whole term is Jacobian. The lambda, that delta H.
That is true. See, okay, so let me explain Jacobian. I will have to switch to my Linux workshop, Linux workstation for a moment for the rest of the lab. But let me explain the Jacobian. See, the concept of Jacobian is very simple. First, think of single dimensions. What is the Jacobian? Hang on. Jacobian. It refers, of course, to the Jacobi brothers. So suppose you have a function y is equal to fx, right, in one dimension.
Okay.
So now the sensitivity to a small change in delta x, you'll give it simply as delta y is equal to df dx delta x, isn't it?
Right.
Right? This is very straightforward, a small change in that. So now now what happens is, suppose y is a function of f x1 x2. Now what happens? Now what
Could
happens is delta y is equal to delta f. A little bit, it will vary. It will have some change because of the response to changes in x1 plus some change x2. Would you agree with this?
right.
Yeah. And now let's make y into a vector. So suppose there is y1, y2, right? So suppose this was y1. So now you have delta y1 is equal to df. Now what happens is we can now think of y1 as y1 is equal to f1x, 1x2, and y2 is some other function. Let me just call it uh, g. Let me call one the f and the other g, or let me f and g, x1, x2. Are we together? So you would agree that this is still the same delta x1 plus df dx2 delta x2. What about y2? Delta y2 is dg dx1 dx1 plus dg dx2 delta x2. You realize that suppose y has, there are two different y's components. So they will independently vary with respect to changes in the x-axis,
Correct.
This is it. So now this entire thing, you can actually write it as a Jacobian. This thing, do you notice that this thing here is, so you can say delta y1, delta y2 is equal to df dx1 df dx2 dg dx1 dg dx2. This thing applied to delta x1, delta x2. Right? You can work out the matrix decomposition. So all I did is I took a matrix out of it in writing it this way.
Uh, c- can you scroll up a little bit, sir? That I just wanted to see that term, the one you have written. If
Where?
little up, little more.
Little up. Yeah, I'm coming to
I
that.
get
So
that
this
one.
is it. This is it. So this is H, right? So now, but anyway, but before that, I'm just explaining to you what a Jacobian is.
Mhm.
Now this, so you agree that I can write it like this, right?
That's right. It is
So
like
nothing
a
but a
standard
matrix
matrix.
representation of what I wrote just above.
Right.
And therefore, this is called the Jacobian.
Okay.
That's it. So it basically says that each part of the output, how sensitive it is to each part of the input, right? So now come back to your autoencoder. Just look at the encoder part.
Mhm.
This is F, right?
Right.
And H is the output. And this is X, right? Basically, the Jacobian is, so now H, let's say that H has two pieces, H1, H2, just as your example, right?
Mhm.
Or maybe an X has three pieces, X1, X2, X3. I'm taking an example, right? So
Right.
now what happens is I can say that I have two functions. H1 is this value here is f1 of x vector, and h2 is some other value, some other, let's say what you would call g there, of the x input, right? And once again I can create this matrix. The Since f1 and h1 are the same, people often just write it as the output, the response of the output. By output I mean just the latent representation h. Yeah. H1 dx1, right? dh1 dx2, and then I can talk about dh1 dx3 dh1 dx2 H2, yeah, DH2, DH1, X2, you realize that all I can do is I realize that this component is the one, because then I can write delta H is equal to this thing, this Jacobian, times
Mhm.
delta times the delta, and I'll just write it in vector notation, the delta X vector, isn't it?
Correct.
So this thing, if you notice that it is what? It is made up of terms, which is the derivative of the output with respect to the input, isn't it? That's what the function is. These are
Yeah.
all derivative terms, right? Component-wise derivative, right? This Jacobian. So one notation that people use in the literature is, they say that it is just a generalization, a vector generalization of the this. This is this. This is it.
That's right. That's the matrix representation of the whole differentiation part. But in the equation above, there is lambda as well. Because why I was
Oh,
confused.
lambda is the suppression term. So okay, let's go back up. So good point.
Right. So the
See what
question is
happens
on
is,
the suppression part, like because if we keep the term more, that means it will be less sensitive. Like it depends
that
how
is
we
that is
manipulate that.
so see what happens is, if lambda is very strong, it is emphasizing insensitivity. It is damping down, it is making H very insensitive to changes of the input, right?
Correct.
So you don't want it to make it too big, because if you make it too big, the neural network will say, okay, I give up. H is constant, right? The minimum loss is when H is constant, and you don't care for this loss. Even if even if the reconstructions are poor, no matter. But this part is the reconstruction loss. So what you want to do is, you want to find the middle ground in which the reconstruction is very good, but your reconstruction is not sensitive to small changes of the input.
I see.
That's all.
So is there any, like, how do we decide that part, like the
The
value as
hyperparameter of the model.
it will be obviously between 0 to 1, but it has to be based on experiment.
Yeah, see, it also depends upon the degree of noise in your system. See, if your system has a lot of noise and you want to still not be unstable, what will you have to do? You will have to keep your lambda pretty strong, because at that moment you would rather be able to reconstruct something
Mhm.
than be unstable.
So application is specific as well here.
Yes, data specific. Yeah. So you have to play with data. Remember, always it goes back to the old saying, right? Data is king.
Correct. Thank you, sir. Yeah.
Right? So, guys, just bear with me for a moment. What I will have to do is I have to get to my other machine and work from that. Yes. And
Asif, one more quick question on the context before we switch to the lab.
haha,
So looking at the two, I'm just focusing on the two examples that you had for autoencoders. One, the denoising one, the other is the contractive encoder.
yes,
I'm assuming denoising autoencoder would be suitable for, let's say, situations where I have a grainy image and I need to extract meaningful content from a grainy image. Building a denoising
no, sorry.
autoencoder would use.
I lost you for a little bit. I apologize. Could you say that again?
I'm trying to look for an example to map each of these and build an understanding. So for denoising and autoencoder, I'm assuming
Yeah.
it'll be useful to have a denoising autoencoder if I expect grainy images, and it can be used to clear out the grainy part of the image. Is that a valid assumption?
That is a perfectly valid assumption. That is one. Remember, it also fills in the blank. One of the things you do is, if you take an image and you hide a part of it, it will learn to interpolate.
Okay. Yeah. So the grainy image could have been some lossy compression happened. And when I got it back, when I decompressed it, there were some lossy areas, and
Yeah.
the denoising autoencoder could enhance it.
Could
Correct?
enhance the image. And both the contractive autoencoders also will do that.
So I was trying to make a difference for the contractive. So the way I was trying to understand the contractive encoder was,
Yeah.
if I have a situation of trying to interpret alphabets and they're written by different people, there
Yeah.
could be variations in how the alphabet is written.
Yeah.
That is a good case for using a contractive encoder. Is that correct?
Yes, 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 certainly.
Okay.
So pretty much, you will see that is literally our lab today, huh? You will see that in a moment.
Okay. All right.
So
Thank you.
guys, give me a second, Prachi. I will join the. Oh, I'll join as another Prachi today from the other machine. So can you guys still hear me?
Yes.
No problem.
You can hear me, right? So now what I am going to do is you have to, one second, you have to tell me. Okay, you have to tell me what you see when you see this. Which screen am I sharing?
The planet and the clock.
Oh, the vertical one. No. Desktop 2, desktop. This one. Okay. Now, which one am I sharing?
A Zoom web browser.
This is better. Okay. So now what we will do, sorry, autoencoders. So this is your lab for today. I will increase the font till what happened? Yes. I'll increase the font and let me know when the fonts are big enough for your screen. Is it big and clear, guys?
Yes.
Okay. So this, just as a background, so let us say that I have a function f that takes the input x and makes it into a hidden representation. Then this is your function. This is the f that I was writing in the writing board a moment ago. And then you need a and then the point is that it's a lower dimensional presentation quite often, except when you use a overcomplete autoencoder. That too is possible. But your basic intuition should be that it's a compressive form like this. Now, if you take a unit activation function and you don't have any other hidden layers except the latent layer itself, you come to something that is essentially equivalent to a PCA. Right? Not exactly the PCA, but essentially equivalent to it. And then you need a decoding function, the G, that will blow up. So remember, neural networks are just functions, continuous differentiable functions in some sense. So there it is. You recover your input. It will come out as X prime. It won't exactly match. And so now your loss is, in the simplest autoencoder, your loss is the gap between the input and the reconstructed input, the output and the reconstruction, X prime being your reconstruction. Are we together, guys? Does this all look very obvious now so far?
It's fine.
It is fine, right? Okay. So now there are many variations to the autoencoder. We have the regularized autoencoders, the sparse autoencoders, the denoising autoencoders, the contractive autoencoders, and these are all the autoencoders. And then the variational autoencoders are a completely different beast. Even though they follow the architecture of autoencoders, they're generative models. What they do is they hypothesize that the hidden representation can be, for example, constructed as a set of as a mixture of Gaussians. Then your only job is to find the use variational inference to find the best matching values of mu and sigma for, I mean, where exactly the bell curve is sitting, or the bell hills are sitting, rather, Gaussian hills are sitting. That is that. So in this workshop, you'll realize that I've given you some code and we'll get through some code. Before I go into the code, I will just walk you through what imports you need. So by now, this import should be looking very familiar to you guys, right? What will you do? You'll change it to your own computer's value wherever you have downloaded the project. So the only import is this. These are the three new classes and one file, vanilla encoders, that I have added to your project.
Asif sir, can I ask one more question
Yes,
before?
please go ahead.
So, in the generative versus discriminative model, in the generative model, when, like, is it always generates the data, like input data um, based on the parameters? Like how exactly it works in different forms when we talk,
Okay.
when we say a
So I'll
model is
refresh it to you. Pradeep covered that. I'll refresh it for you. See, in a discriminative model, right, all you care for is given the input, given a certain input, what is the output?
right,
Right?
right,
Let's take a classifier model. All you care for is what is is it a cat, more likely a cat, or a dog? Is it more likely a cow or a duck? Right? Given
correct,
the input. So you just care for the probability of a label given the input, and whichever label has the highest probability, you'll pick. Right? Now, in a generative model, you go one step further. Generative models are also models capable of making predictions or being discriminative. But you do one extra step. You say, no, wait a minute. I don't want to just figure out whether it's a cow or duck. I want to figure this out. In the feature space, like the feature space of weight and height of a cow and all the features of the animals, what is the probability distribution? What is the shape of you know all the cow data? And what is the shape? What is the probability distribution of all the duck data? Are we together? So if I know the actual probability functions in the feature space for a cow and for a duck, anytime you want a cow, I can generate a completely new cow for you. All I will do is I'll sample from that distribution, isn't it?
right. So it does, in addition to constructing the input, it will anyways do what the discriminative model can do.
Yeah, which it can do. So for example, if I get an input, all I need to figure out uh, at that point, now that I have a probability distribution for both the cow and the duck, which of these two have a higher value?
Right, right. It will know
And
that.
so it definitely implicitly is automatically it is a discriminative or a classifier, but the generative part is that it goes above and beyond that. That's why generative models are a little bit longer to train and more computation, more data needed, because they go further. They try to figure out what the underlying distribution in the feature space is. Okay. And once you figure that out, you have the lovely thing. You can go on generating data, and that those in practical terms have far-reaching consequences. So for example, you can take two faces. If you have faces, right? You can basically say that find what these two faces map to in the latent feature space, and then find all the intermediate faces. Give me 100 intermediate faces in a continuum from this to that guy, right?
Right, right,
Right. So, for example, you can take Pradeep and you can take Amitabh Bachchan, and you can put a continuum in between.
right. That's true. So they have much more usage.
Much
Like,
more use for that. So generally, when you have a generative model, you have a bigger success. You can find many practical uses for it.
got it. Got it. Thank you very much, sir.
Nice. So guys, there are four classes I wrote for you. The base class is the real one and we'll walk through the implementation. But imagine that it's an autoencoder. Right? This is the signature of the autoencoder. We need to know the input dimension, right? We need to know the latent dimension, like of a data, and we need to know if you want to give a lot of hidden layers, how many hidden layers you do. So I have implemented the autoencoder in such a way that you can specify many hidden layers. People often call those hidden layers, right? Autoencoder with many hidden layers. people often call them the stacked autoencoders in older literature. Nowadays, you don't see much. You just assume autoencoders will have many layers in between. Right? So this is it. And now you give the hidden layers as just a list. You can say how many nodes you need in each layer. So here we are talking about fully connected layers, FC layers. So the way to use it, and first at this moment, just play with it, guys. See how it works. So here I've instantiated your base autoencoder. I'm saying input dimension 28 square. Now, what does the word 28 square remind you of? What is 28 by 28?
Furrow.
Come again?
The furrow.
I didn't hear that.
The furrow image. Dimension.
FRO image, is it some particular data set?
MNIST.
Oh yeah, MNIST, certainly, yes. It is the MNIST data set. Yes, MNIST, Fashion MNIST, they are all standardized to 28 by 28. ImageNet is 32. Now people are creating 64 by 64 images and so on and so forth. So you can pick. At this moment, I'm going to do the lab with MNIST. And your homework is to try out other data sets. Now, my latent dimension is 16, right? What does that mean? It means that what does that mean? My hidden representation, latent representation, is a 16-dimensional vector. So we are going from 784 dimensions to 16 dimensions. So as you can imagine, that is a massive dimensionality reduction. Do we agree?
Definitely.
Yeah. And so what you do here, I printed out and I've created a utility function so that if you print out the autoencoder, it will declare itself. And here it declares, it says the encoder is made out of, do you notice how the numbers keep decreasing? 784 to 64. And what it has done is it has automatically figured out that it's a pretty steep dive from 784 to 16. So helpfully, it has gone and added a hidden layer, one more hidden layer of 64 dimensions. So it is 784 to 64, 64 to 16. How did I come upon 64? It's very easy. You take the log base 2 of this, log base 2 of this, these two, and find the middle point. Okay? And you'll see it in code in a moment. So that's that. And then a decoder is just the reverse of the encoder, except that at the output of the decoder, output, so you notice that everywhere there is ReLU, but in the output, there is a tan edge. Why tan edge? Because the MNIST images, we have standardized it to the scale of 0 to 1. So there are two ways of getting values in 0 to 1. Either you can use sigmoid or you can use tan edge. If you remember, I mentioned that tan edge are much easier to train, faster to train, right? But sigmoids are very slow to train. Do you guys remember that from our earliest, one of the first sessions we did? That prefer TANH. If you have to go sigmoid, use TANH instead. You could have used sigmoid, it would have worked just as well. But this is it. So now you train the network. Here I am just training the network.
Can you take a moment to explain once more on the hidden layer? So why did you decide on the hidden layer? What was the motivation for it?
See, by adding hidden layers, you optimize, you make the learning more efficient. If you think about it, uh, you need not have had hidden layers. Huh? The original autoencoders were like that. Then what happens is, and your universal approximation theorem and all of that, but basically you will get some representation, latent representation. But the learning there is not as good. And you can play around. This is actually your lab, your homework. By adding hidden layers, you do much better. Right? At this moment, I've added only one hidden layer. You can choose to remove it and just go modify the code and remove that, or add more to it. And this is something we'll do as a homework, add more and more hidden layers. See, the whole point of deep learning is when you add a lot of hidden layers, if you can successfully add it without having your vanishing gradients and other problems, if you can add more hidden layers, the more efficient is your learning. Right?
Okay.
So instead of making very tall neural nets in which each layer has gazillions of nodes, you prefer making it out of many smaller, many layers with more modest number of nodes. In the case of autoencoder, it becomes a direct choice. You're starting with 784 and you're diving down to 16. So you have a lot of freedom to stick in many more layers in between of smaller and smaller size, right? Funneling down to 16. And the learning is more efficient. Oh, by the way, I mentioned it 8. Please correct it, because initially I did it as to make it 8 is your homework. I shouldn't say 8, 16. It's a typo. So we go from there to 16. You may wonder, how did I come up with 64? So we'll obviously, you can look up my code and see. Then I've made this, see guys, I've made the API very easy. You instantiate the autoencoder, you see how it looks like, and then you ask it to train itself. By default, it will train itself on uh, 5 epochs, right? So when it trains itself on 5 epochs, you can see we always,
Asaf,
yes,
uh,
go.
there is an error in the training line. Um,
I get an error too.
yeah, it goes back to the vanilla encoder Python file. I'm not able to understand what it is.
Yeah, I
I think
see
it
messages.
yeah, it is related to the size of tensor A, not matching tensor B.
Okay, I
784
will
versus
split with you.
20.
Let me just let me just walk through, and then I'll make sure that it works on all your machines.
Do you see the same error message that I put in the chat?
Let me see what you guys are putting in.
In the
I
chat,
don't
in
see.
the Zoom chat. I didn't
Oh,
put
in
it in
the
the chat.
Zoom chat. Okay.
Sorry.
Yeah, the same error.
All right, guys, I'll look into that. Huh? Give me a moment. At the last minute, I was changing the size back to 16 from 8. So something may have happened. We'll look at it. The learning rate, so there's some default values I've put in when you learn, all of which are configurable, the learning rate, the number of epochs. I put 5 epochs. The reason is you notice that by 5 epochs, the loss has stabilized. This is your standard loss plot. You must be familiar with this from your previous labs, plotting the loss. Now let's visualize the results. What do we do once we build a model and it looks good? Let's visualize the results and see if it makes sense. So here, let me make it even bigger. And here, oops, sorry. So guys, this is the original image here. And below it, below every original, first row is original images. And below it are the reconstructed images through the autoencoder. Would you agree that the reconstructed image is a little blurrier, but it is still a fairly good representation of the original? Would you feel that, guys?
Yes, sir.
Right? It is, right? And now you can make it even better. Now here I used a latent representation of 16 dimensions. You can play with it. You can make it less than that. You can make it more than that and so forth, right? What happens if you reduce it down to 4 dimensions? And or 3 dimensions? For example, can you capture the essence of a digit with just 3 dimensions? Something worth thinking, isn't it? Let me ask an extreme question then. What if you go down to 1 dimension? What happens? So as you play with this, there are some surprising findings. And I thought that I'll leave those findings as some fun things or some pleasures to be had as you do the lab. It is quite amazing actually how data can live in, or the essence of the data can live in much, much lower dimensional spaces. It's just amazing. So I want you guys to please play with these images and see if you can, uh, with this autoencoder, and see what you can do. Now, here's the, and by the way, I'll take you guys through that bug, huh? Whatever it is, we'll fix it in a moment. Now, first thing is, see the effect of reducing the latent space or dimensionality. This is very easy. You can just go here. What do we need to do to change the dimensionality, guys? Latent dimensions, you can make it something, make it 4. Make it 3, make it 2, see what happens. Make it 5, 8, see how it varies. Then the other thing you can do is, so see what you can do uh, and how much it degrades your images. The next thing you do is, how about adding more and more hidden layers? So in the vanilla version, you didn't give the hidden layers, so it automatically picked 64. But suppose you actually explicitly give a few hidden layers of different sizes, then what happens? I used ReLU as the activation function. What if you change it to CLU? What if you change it to something else? So try it out, guys. Play with the different activation functions. See what it does. Look at the runtime, how slowly or fast it learns. What if you just make it a sigmoid or tanh for learning? See how well it learns. Then does increasing the number of epochs have visibly better reconstruction of images? Check it out. What happens if you set the number of epochs to 50? Right? You should get some hint just by looking at this graph, but try it out. Right? Try it out and see what happens. Then other thing is, I've tried it with MNIST, right? But a fashion MNIST is a drop-in replacement. And it is a drop-in replacement, as in your torch vision also comes built with it. Instead of saying MNIST, you just have to say fashion MNIST. Fashion MNIST is a collection of dresses, shoes and dresses. So you have a bigger data set to learn from. You can try that out. You can try it out with CFAR and CFAR 100, CFAR 10 and CFAR 100. Do you guys remember what was CFAR 10? Anyone remembers?
Yes, another image data set.
Yes, with 10 classes. And CIFAR 100 is 100 classes. They are all subsets of the ImageNet dataset. So that is that. Then let's look at, so this is easy, and we'll walk through the code in a moment, but let's first be just the user of it. You can use a denoising autoencoder. So this time around, instead of giving it the input, we'll give it the input and we'll sort of add noise, inject noise into the input and see what it does to this picture. Right? Now, if you notice that here, what I've done is something quite surprising. I have reduced it down to 8, output dimensions to 8, and I've added 3 hidden layers just for fun. Why did I do that? For no particular reason. It's just playing around and seeing that you can do that. When you do that, this becomes your architecture: 256 to 64 to 32 to 8. And 8 goes back to 32, 64, 256, 784. Right? So these are your thing, input, hidden dimensions. Then I'm storing the data in a directory called noisy. And when you do that, you can give whatever names you want, some directory to put it in. Well, here is the loss function. And the interesting thing is that, let's look at it. And this picture I find quite amazing. So guys, would you agree that here, actually, let me make it just a little bit smaller. Oops, sorry. Yes, so we can see all of them together. Look at the picture, the first column, 9. Can you guys tell that the middle one has noise injected in it? It's noisy. Uh, can you make out the noise that I've injected into this image? I don't know if on Zoom
Kind of
it comes.
fuzzy, so maybe it's Gaussian.
No, no, no. It is a straightforward noise. So see, look how clear the 9 here looks. Sorry. How clear the 9 here looks. And do you see the dottiness, little dots all over the place? Okay, hang on.
In the background, you had added white dots.
Yeah, that's right. In the background, I've added white dots. See,
It looks like a white noise, basically.
it looks like white noise, exactly. And then you look at the image that we have reconstructed. Do you see that the white noise is gone? Like, let me make it bigger. I don't know if over Zoom this comes through. Can you see, guys, that this noisy image has been completely cleaned out,
Yep.
Correct.
right? So this is the beauty of it. You can give a photograph on which you have poured coffee and there are coffee stains, and a denoising autoencoder will clean out and remove your coffee stains for you. Right? And if you look at it, it is quite decidedly different, right? Look at the zero here and the zero here. It is much more cleaned out, right? So that is one purpose of an autoencoder. Now let me just decrease the fonts a little bit. Okay. So this is the value of the denoising autoencoder. Sorry, I am jumping around. Yeah, denoising autoencoder. Right. By the way, I've simplified the code because at this moment, first play around with it. These are all one-liner codes. Huh? To train, you just have to say train, and then you can plot the loss, and then you can just visualize these images. Once you do this, oh, so no, I've gone too far below. So there's more to it. Homework. So then this is your denoising autoencoder. Yes, it has done its job. Then you have convolutional autoencoders. What are convolutional autoencoders? I said that we built our autoencoder out of fully connected layers, isn't it? But there is no reason why you should just use fully connected layers. You can use any layers you want, so long as the architecture, the overall architecture is that encoder-decoder architecture. So here, we have built a autoencoder out of convolutional layers. And as you will see with convolutional layers, actually, the results are, in my view, better for images. So I took the three convolutional layers, right, for the encoder. And so if I train it, you notice that the losses are actually, mm, if you look at the losses, 0.01. Let's look at the loss that you ended up with in the previous ones. Do you notice that when you train, uh, hang on, a normal autoencoder with a deep layer, this is fully connected layers. What was the loss you ended up with? 0.0664, right, guys? This is 0.0664. Relatively speaking, if you notice that when you use convolutional neural net, you will 0.0112, right? It is almost 1/6 of just in the same number of epochs, you end up with an error, which is a loss, which is 6 times smaller compared to that. And we will see whether it leads to cleaner reconstruction. And look at this. Original image and restored image. You notice that they look almost identical, guys.
Yes.
Right? You have to look really hard to see the difference. If you look at this four, the in the middle image, last row, second column, look at this four, and you look at this four here, you will see a subtle difference here. Right? So all over the place, you will see some subtle difference. This 8 in the first image, top left image, the 8 here has a little marking inside it, and this one doesn't seem to have that marking inside it. So it does a pretty good job of reconstruction. Right? And that's the beauty of it. That's why you should use it. And then there is a denoising. Can this, when you use the convolutional layers, can you use it to denoise your images? Very much so. And when you denoise, again, it does a better denoising. Um, Look at this. It's the same code. Essentially, I'm using a different class, a different autoencoder. Now, notice that this is, look at this. Here, I hope you can see the noise here. In this picture, are you guys able to see the noise that I sprinkled in?
Yeah.
Yeah.
Background like sprinkled snow.
Right. That's right. And so if you compare, you look at this, any noise one, let me make it a little bit bigger. No, a little smaller. Oh gosh, too big. Okay. Uh,
So this is fine.
yeah. I hope you can see the difference between the two, that you have completely removed the noise now, this convolution layer, isn't it? So you give it a noisy image and it will be able to clean it out for you. You have trained it to clean out noise. Now, at some point, I'll give you another lab. Actually, I was going to do it in the vision part of this workshop, where we are going to do, I would give you other things like some parts, somebody's ear masked. You take a face, the nose is missing, or the ear is missing, or something like that. And you see that the autoencoder goes and paints a nice, fills in a nose, or fills in an ear, and things like that into the image. And it is quite magical actually to see how well it can go and fill in the gaps. So from a practical use perspective, guys, do you see the usefulness of autoencoders, at least for the purposes we are seeing, the compression and for noise reduction? Any questions before I go into the code?
So Asif, one quick question. The example that you just narrated right now, where
Yeah.
it fills in a nose,
Yeah.
uh, is it filling in a feature, or it'll just fill in based on the local info that it has? It doesn't have
No,
the
no, no, no.
notion of
It
features,
fills
right?
in not based on local info it has, but it fills in based on the memory of all the faces it has seen and learned.
Okay, so it has it's building the memory of the features.
Yes, it brings in a nose, not because there is no nose in the picture. So if you interpolate, it will begin to look like the cheeks, right? But it has memory that this place needs a nose, and it will fill in a nose.
Okay, okay.
It's quite amazing, actually, the autoencoders, the way they work. And I always find that remarkable. Yeah, I mean, I'm sort of exaggerating the fill in the blanks part of it. You just hide a part of the nose, it will go fill in the nose.
Yeah,
Right?
thank you. Yeah.
So it has a memory that this is what it should look like. And that's a very sort of a hand waving way of putting it. Right? But still very remarkable, actually. I've always been very fascinated by the power of autoencoders, especially, and then variational autoencoders with their generative capabilities, just remarkable. So guys, what I will do is we will look into, some of you are having struggles with the lab. What I would like to do is go over the code quickly and then give the last hour to make sure that all of this is working on your machines also. I think some of you are having little issues. Should we take a 10-minute break, guys?
That would be
Before we
fine.
go into the code, let's take a 10
Yes.
minute break and we'll go into the code after that.
All right.
Yeah.
Back at 8:30 or 8:35?
Yes, let's make it 8:35.
Okay.
And, yes. Yeah. Bye then, guys. I'll just pause the recording, or can I pause the recording from here? No, I can't. I'll let it go on. All right, guys, are we here? Can I start?
Yep.
Okay. So let me, which screen should I be sharing? 1 second. Let me solve that mystery first. Okay. So guys, I identified what was the mistake I made. I'll put a patch. What I did is I mixed up the noise and the non-noise part in the loss function. It's a small thing. I'll push the update, guys, right after this. Kate, thanks for trying out the code right away. Otherwise, I wouldn't have
Thank
known.
you.
Yeah, this is good. So what are you guys seeing on my screen at this moment?
Seeing the Jupyter, yeah, autoencoder.
Autoencoder. Okay. So what I will do at this particular moment is walk you through the code. Oh, I should go and turn on the recording, isn't it? Where is that thing gone? This is getting to be a little hard to figure out. Where is the control gone? I'm trying to determine where the controls are gone. This is odd. I can't tell. Please bear with me for a moment. I don't know where the control for Zoom has gone.
So just hit an escape, Asif. That'll take you out of the full screen. Then it should.
Not really. Not on Linux.
Oh, okay.
There's some. Oh, stop. Okay, here it is. I'll start the recording now. Resume recording. So if you notice in the code, you'll find a directory called autoencoders, guys. Huh? There is only, actually this thing can be deleted. It is not there when I gave it to you and I need to update it. You won't find these directories. I cleaned it out because when you run your code, all these other data directories will get created. This data directory is where the MNIST, when you run the code, it will download the MNIST data. This is where it will get stored. These are all your output image directories. The only thing that you need to read is the vanilla encoders.
Wait, Asif, one moment. You said the MNIST data will get stored in a directory called data will get created?
That is right. Because when you look at the code, you'll see why it is.
Okay, that didn't happen on mine. So I need to figure out why. Okay.
Yes. Okay.
Yeah, I don't think we have that minimal data in the svlearn autoencoder.
Okay. So we'll see that in a moment. Let's see. So guys, let me walk you through the code. Should I walk you through the code through Jupyter, or would you, is this visible, like this black thing? This is PyCharm. Is it too small on your screen?
And Jupyter
Okay
is
with
better.
either.
Jupyter was better.
Jupyter was better. Huh? So let's go through Jupyter. Huh? So this is your code. As usual, I've written the code in classes and objects and so forth. So the reason for that is you don't repeat yourself. It's very easy. When you create a base class with all the common functionality, then creating other encoders, you just reuse that class and you write just the deltas, the small differences between the two base class and so forth. Of course, the downside is if you are not careful and you're trying to do like I was doing, somewhere along the way, you'll end up breaking everything. So I need to go back and fix it. It's an easy fix, I'll fix it. So this is, anyway, the base encoder. Let me explain what it is. The input dimension is, of course, the input dimension, latent dimension. Hidden layers, by now you know what it is.
Okay,
These
so
are,
only supposed to have that vanilla encoder py file in the svlearn autoencoder directory? Because
yes,
I've
yes.
got the init py, vanilla encoder.py, nothing else.
Yes, that is the only file you should have in that directory.
Okay.
Yeah. When you run that, other files will get created. Right. So actually don't bother at this particular moment. I gave you a very clean data set, I mean clean project with all the unnecessary directories and files removed. So let that be as a library. So here we go. I will again explain this. So this is line 41 to 47. I hope is self-explanatory, right? You don't want the input dimensions to be one less than two, because there's no further compression you can do, right? Uh, if latent dimension at this particular moment, we are not doing the over complete autoencoders. We are just assuming that these are under complete. The hidden dimensions are less. The if latent dimensions are less than input dimensions. So line 44, guys, is that self-explanatory? I hope so. Then obviously latent dimensions people can't specify to be less than zero. So these are just sanity checks. These in programming, it's called a preconditions check. You don't want to build an autoencoder which is strange, right? So if you notice that the user has not specified any hidden layers, then what I do is this is the bit of code that I mentioned, which comes up with at least one hidden layer, whose size is a good one. I take the log of the input, log of the output, take the average of the two, and of course then I exponentiate it back, right? So I come up with a hidden dimension there. That's how I came up with 64. This is it. These are just storing it. And by the way, this is, I just added it just now. You won't see it in your code. It's because of the fix that I'm putting in for you guys. I mixed up my with and without noise situations. That's why we're having this issue. So there we go with noise. I'll give you an updated version of this file. The forward pass. By now, guys, who would like to explain what the forward pass does? What the forward method does? Anybody would like to explain? What does the forward method in PyTorch do?
Creates the feed forward network.
It is literally the inference part. You know, you give it an input, output comes out. It does all your matrix multiplications in the forward journey, right? So it will do the encoding and the decoding and return it. Right? The wrapper is just a helper. It just, you know that when you say print on this object itself, it should print out the things properly, which is what it does. Build encoder. Here is how I build the encoder. And this is something that is worth paying attention to because I introduce a new syntax here. This syntax sequential, I was waiting to insert it somewhere in your thing. It's a little bit like Keras. It helps you make your neural nets pretty efficiently. So what we do is I decide what my layers are. Let's walk through the layers. We agree that the first layer, there is no choice. It has to be this input dimension. The input dimension will be the size of the first layer. Do we agree, guys? Because it's the input layer. And then what will be the output layer, whatever the size of the first hidden layer is, the output to that, right? Then the first layer, we are activating it with a reloop. So this, by the way, I'm just adding it to a list at this moment. I haven't built it. I'm creating these little pieces and I'm adding it to a list. So far, so good, guys. Does it make sense? Guys, give me a feedback. Does this make sense? Is it very easy to see what
Yes,
I'm?
sir.
Yeah, this is easy, right? After that, what I do is we have a lot of hidden layers because I gave the functionality that you can have as many hidden layers as you wish. And now I need to dynamically figure out what those hidden layers are and add it to this modules list, which is what I'm doing here. And then finally is the innermost central layer, which is the which will be the output here. Now what do we do? Here is your latent. This is the at the encoder. The actual layer, I should have called it not encoder, but the latent layer. This is your latent layer, right? The hidden layer -1 in latent. After that, what do we do? This is a syntax and then sequential. You give it a list of these pieces and it will stitch them together into a neural net. Right? So which is what I'm doing. So this syntax will be a bit new to you. By the way, what does star mean in Python?
Variable number of arguments.
Say that again, Shankar.
Variable number of arguments.
No, basically, if you give it a list, it will
It will give the object.
unwrap the list and make them like a variable art, like you are saying, right? It like someplace sequential is expecting literally an unwrap list, like you can go on adding things to it, and so it will take a list and it will unwrap it. And a double star unwraps a map. Single star in Python unwraps a list. So this is it. It just so happens that the sequential takes arguments like that. So we do that. So how do we build the decoder? Remember, I said that the decoder is the reverse of the encoder. So one second, guys. There's a train going by. So please bear with me. All right. So one of the common things I notice people do on the internet is that they will just repeat the encoder backwards, the code of the encoder backwards in the decoder. The trouble is, then if you change your encoder, now you need to go and change your decoder. You know, if the decoder is a mirror image of the encoder, why repeat yourself in backwards? It's a bad idea. You can introduce bugs in it. So try to do it the way I did it, or some other better way. Uh, what I did is that I took the list of modules that I have here and I have just reversed it. Do you notice that? This is, by the way, a very Pythonic way of doing it. This creates a list that is the reverse of the hidden layers list, right? So now what happens? Instead of each layer being smaller than the previous layer, now each layer will be bigger than the previous layer in the hidden in the reverse list. Does that make sense, guys? So suppose you go 256, 64, 32. What will be the reverse of it? 32, 64, 256. Isn't it? That's that. So I take a reverse and now what do? I repeat exactly what I did before, but this time around I weave it out of these layers and I put it. The only thing to note is that in the output, the last activation is a tanh, right? And the reason is we want values essentially between 0 and 1. And what we do is we tanh produces values between -1 and +1. We can always shift and scale it. If you add 1 to tanh, it will go from 0 to 2 and then take half of it. It will become, like, for example, you see me do it here. So that explains the encoder decoder part. There is a helper method, shape to image. What it does is, if you see, the point is that if you like take a 28 by 28 image with one channel, which is the monochrome channel, it is basically a three-dimensional object, three-dimensional tensor. When you take the three-dimensional tensor and you flatten it, because a dense layer can only take a linear input, isn't it, guys? That's why in PyTorch it's called linear. Means it can only take a vector as an input, not a tensor. So how would you flatten it? You would just flatten it into a single vector up to 784 dimensions. When you flatten it to a 784 dimensions, you do all your work. Later on, when you are looking at the result, you want to shape it back to an image, isn't it? So this undoes this. So this X, you imagine that it's a 784 dimensional vector. Now this vector we want to shape back into an image. Actually, it's not really a vector because there is one more thing there. The mini batch size. The mini batch, let's say 32, means that it will be 32 cross 784. But that 32 is implicit. The linear, the PyTorch works transparently with millibatch. So you don't even speak about it. You just refer to the fact that the rest of it is a vector. The other dimensions are vector. So now this is here. What we do is we shift it back. You remember tan h produces values between -1 and +1. We need values between 0 and 1. Why do we need values between 0 and 1? Because the MNIST, we standardize it to 0, 1. Right? So if you want to compare input to output, we better be on the same scale. That is it. This is not needed. It just makes sure that if we used any other activation function, then uncommon disguise. If you use something that produces values above and beyond, if it or does something strange, then you may want to truncate the values to 0, 1 interval. Then you know that this data, when it comes, it is actually initially a two-dimensional vector data. It is the batch size times one dimension is the batch, the other dimension is the batch size, and the other dimension is the actual data. Right? So for every batch element, there'll be one vector, one image. Yeah. So imagine 32 images coming together through this in this shape. You're shaping 32 of these images. You're trying to do that. So what do we do? What we do here is, how do we find the batch size? The rule in TensorFlow is, in the image tensor at least, torch vision, the tensors are annotated like this. First, the batch size. Second, the channel. Third, now comes the image size, height and width. Yeah. So, so the zeroth element, which is the first element, would be the batch size. A channel is one. We know that the channel is one. It's monochrome image, right, at this moment. And by the way, this you'll have to change when you try other data sets. I'll leave that as an exercise for you. You'll have to change it to 3 or something like that. Now, we know that ImageNet data is 28 by 28. So what do we do? This is just a view. You remember this is the tensor PyTorch standard function. Any tensor you can reshape to any other tensor. So here it is. We do the view and you give it the batch size, the channels, image size, height and width. Right? So now what will you get? You will get images, right? 32 images showing up and so forth. That is that. That's all it is. Right. So how do we build? And by the way, this was where the bug was. I need, so no, this is not the bug. I'll tell you where the bug was. Okay. A build input. In
One, see, from the previous function, can you touch upon why you had the static method?
Oh, it's Pythonic. It's a bit Pythonic. See, do you notice that this this function, it does not need any member variable, any property of the object or the class to work with, right? When
Okay.
a function is invariant to everything, you give the facility for it to be called
From anywhere. Okay.
yeah, anywhere. Right. That's
Okay.
that is it. So it becomes like a C function. That's what it is. You notice that it doesn't have self as the first argument here.
Okay. Yep. Thank you.
So a build input is simple. Suppose is the opposite of that. Suppose I get an image 28 by 28. What do I need to do? I need to and let's say batch size 32. So it will be 32 times 1 times 28 times 20 by 28, right? So what you do is you linearize it into one linear vector. The way to linearize it would be you take it and then you for here you keep the number of dimensions. Of course, that's a number of batch size. That's a mini batch. You ignore that. And the rest of it, what do? You put a -1 means take everything and put it in one long vector, right? Which it does, and we can print it out. You can see it. This is the fix I was putting in your code when in this break. It's a minor fix. I'll give it to you. So let's now look at the train part. The training part by now you should be very familiar with. Right? Self batch sized. So I assume a default batch size of 32. Right? Now, those of you who attended my loss function, loss landscape thing, you know that batch size, how do you decide a good batch size? If your batch size is 1, it is stochastic gradient descent. If your batch size is, let's say, the entire size of MNIST, well, then it's just gradient descent, a batch gradient descent. But typically you do mini batch gradient descent in between. Sizes of 8, 4, 8, 16, 32 are common. 32 is pushing it. Sometimes you go for 64, 128 also. The bigger the batch size, there are two problems with it. One is that you may not have enough memory on your video card. That is one issue. The second problem is uh, bigger batch sizes introduces its own instability on the loss landscape. So you have to be careful. Batch size is a hyperparameter of the model. In the autoencoders, it doesn't matter terribly. 32 was a reasonably good number, and I took it. Epochs. How many epochs I trained for? Just in this particular case, you know that it easily trains into 3 epochs. 5 is pushing it. Learning rate, you can play with the learning rate. As I told you, learning rate is a hyperparameter of the model, right? And you can play with it. Of course, you can do better things like one cycle learning and all that. But at this moment, I've taken a fixed learning rate. Now, the output directory, where is it that you're going to put your output? The images, as it is learning, it will keep outputting some output images and so forth, where it is. So this is it. And show directory is, those of you must be remembering from past labs, it is just my helper method that makes sure that that directory exists. If it doesn't exist, it creates it. Right? Because you may specify a directory that may not exist. So it's just a convenience. A transform does what? It just converts it into an image. For MNIST, normalization values half are good. These are monochrome images and 0 to 1. So you normalize it on a scale with the middle being half and half. So this is the point of where the data is stored. You know, I've written tilde data means your home directory and create data. So right. So when you do this, your MNIST data will be downloaded to your home directory if it is not already there. Download is to make sure that and once the data comes, you apply these transforms. So your data set now is made up of tensors. This is the data loader part. So remember, what's the difference between the data set and the data loader, just to whet your recollection. If you think of the data set, the whole data set is a huge pile of sand. Your data loader is the guy with the shovel. Data loader will give you many batches of data. When you ask it for the next and the next and the next, it will take a shovel, and each shovelful, it will give you one mini batch of data. That's the data loader. Loss function, of course, we talked about it, mean squared loss. And optimizer is the one that will help you learn. This is it. Now, this code should be pretty familiar to you from the past. History, loss history is a class that I created to keep track of the losses. You can use it. So epoch. So now what do we do? For every epoch, for all the mini batches, you do the learning. The learning is, you'll realize, very straightforward. It is given, you take the image, now you build input. You know, do I need to linearize it? Do I need to add noise? Whatever it is, do that. And then self on that, because this entire class itself is a neural network. You call this class itself onto the input and you'll get an output. So this will, what do you think this will call? Which of the methods of this class will it call?
Init.
Init
Init.
method.
Yes, no. Remember, the module itself is a function, and the function is directed to call the forward method. Right? So this is a thing that trips people. When you make the neural network, the training inside the neural network itself, you have to call self as a function. Right? If you want to call init, you would have to do self dot underscore underscore init. But when you call the object itself as a function, you can do it only if, as in PyTorch, your class is a functional. Right? So it's a very Pythonic thing to do, guys. So as you become more familiar with Python syntax, you will realize that it has all these nice conveniences, and PyTorch has really been well designed with Python in mind. So this is the part, this is me putting the fix in for the mistake that is happening. I'll put it, basically I sort of muddled up as I was trying to make it for multiple classes. I muddled up my loss from the, am I finding the loss function with respect to the input or the input image, or what am I finding it with respect to? So I need to distinguish between these two cases. That's all it was.
Hey, Asif, the question maybe I should have asked like maybe two lectures back. How, how can I find more about self function? Because I'm a bit confused with the self declaration here in the previous few pages also.
Oh boy, maybe I shouldn't have used this. See, basically self refers to the object itself,
Okay.
right? So in Java, it is the this,
Okay.
except that in Java and in C++, this refers to the object, right?
Yeah.
In Python also self refers to the object, but for one exception. When in Python, a function is an object in itself. So if your entire class is also a function, now how do we know that it is a function? If you look at it, that comes from the fact that, look at this line, line 29. A base autoencoder takes nn.module as input, as a superclass,
Mhm.
right? So what it says is that a base autoencoder inherits from module. Module class in PyTorch is a functional, right? So it is both an object and a function. So if you know that there's a function called x, you can just call x on some input, isn't it?
Okay.
So that is what is happening here. Yeah, this is a little. See, guys, I did it like this so that the total size of the code base remains small, because we are talking of 4 autoencoders. Typically, if you look at the web, you'll find that people write independent classes with completely different implementations. But I have a unified implementation, putting it all together, and you'll see that with this base class in place, the rest of the autoencoders are just a few lines, 3, 4 lines each. So this is the magic with object-oriented programming, right? You make a very good base class with a lot of core functionality. And then all the inherited classes have just a little bit of work to do. So that's that. But I could do it only because I could use I could use, syntax like this. Right? So just think, okay, here is one way to look at it. Forget line 149. Imagine that you are seeing the word self dot forward on the input. Then it would make sense,
So
isn't it?
can you add a comment there so when we
I
go
will add.
back, we know?
Yeah, I will add it. Huh? I will add a comment in the, because I have to give you guys anyway a fixed version. I'll add that comment. Huh? So now what happens? So it's very straightforward. This gives you the forward pass. It produces an output image from the autoencoder. So I'll add a lot of comments in this. I thought that most of this loop you guys are familiar with now. But I'll add more comments. Then this output I need to compute the loss from. Once I have the loss, I need to backpropagate the loss, right? And then the optimizer will take, once I backpropagated the gradients of the loss, what do? Optimizer takes one step forward, means updates all the weights. Then the rest of it is just bookkeeping. I'm storing some information. And, some of the files, do you notice that I store some files into the directory? So that's how I visualize it in the Jupyter notebook. I save these there, right? The plot loss function is literally the plot loss that you're already familiar with from your classifiers and other things. So I've just reused it. If you look at the plot loss, it is simply reusing the plot loss that we already created. Remember those days long ago when the classifier, when we were writing a regressor and classifier with deep learning long ago. So all of that code is being reused. That is your training. Where is it? That's a main training loop, right? This is it. You plot the, so this is the beauty, again to the point that once you have created a function, reuse it. That is why I encourage you not to put everything in Jupyter notebooks. It's very hard to call function written in one Jupyter notebook from another Jupyter notebook. But if you write it as proper Python library, then it's very easy to recycle code or reuse code. So now I did that. See guys, look how easy is it to create a denoising autoencoder. What do I need to do? I just need to insert the noise, isn't it, into the input. So what I do is before I feed it into the input, I have just one method here, build input. So you give it a data, it will take the data, it will do whatever transformation needed, like for example, linearizing it and so forth. And then what it will do? I'm just adding, at this moment, I'm adding just random noise. You can add Gaussian noise, you can add sparkle noise, you can add whatever noise you want. But just as an illustration, I add random noise. Right? And you can decide how much noise to add. For example, you can add a 10, by default, I add 30% noise. That's a pretty aggressive noise. Or you could add less or more. Right? Don't go like 90% or something like that. It will destroy your thing. Uh, that is it. So do you notice that when you have classes, I managed to create a denoising autoencoder literally with only like one, two, three or four lines of actual code, see, from an autoencoder. And that is why it is of value. Now I can build an autoencoder out of convolutional layers instead of a feed forward or linear layers. If you look back here, the default autoencoder I created out of linear layers, right? Where am I? Build encoder. Yeah. Do you notice that everywhere I'm using linear layers? Linear. What are linear? These are fully connected dense layers. You don't have to use that. You can instead use convolutional layers. So here it is. And once again, because I have my base autoencoder class in place, using this is very easy now. By the way, you always search for good, layers, and it comes through a lot of a trial and error, right? So I just took it literally from the Toronto AI group. They had this example for the autoencoder. It works very well with MNIST. Obviously, these numbers you come up to by playing a lot. So instead of cooking up my own numbers, I just took the actual layer values from this particular link, this lecture, this link.
I say one other question, right, on convolution network layer. Could you describe what exactly that? Or
CNNs. Oh, okay. This is a see, convolutional are like, think of them as filters or stencils. So suppose you have a page in which you have a stencil mark, X marked, X cut out, and you go over the wall or over some surface and you look for a match to that X as you move that stencil uh, all over the surface. Somewhere it will match, right? Let's say if there's an X on the wall, it will go match it.
okay,
So now you know the location of a X in the image. That is the basic intuition of a convolutional filter. Right? This process of applying that stencil to the wall is called convolution, and then seeing if there was a match. That is the intuition of convolution.
okay.
Right? So convolutional neural net we covered in part one, and I just remembered that you weren't there in part one, were you?
I wasn't here.
Yeah, that's right.
That's why there's all this relu and I'm getting like lost
Right.
when he's talking.
Yeah. All right, Shini. Learning is a cycle. You'll come back to it again in March, February, March when I'm teaching it. It's not too far off. Join the next batch again.
Okay.
So by the time we finish this, you'll be ready for the next batch. All right. So this is all I'm doing is convolution. Now here you have to see the how many filters to how many channels and to have or filters to have in each layer. The basic rule is the number should keep on increasing. Right? You see these numbers increasing? That is it. The size of the filter also is increasing. This is a very common thing to do when you are dealing with convolutions. Now, what happens is that if you look at this thing, we are not using max pooling here, right? In this example, take this as a homework. Go add a few max pooling layers in between. So when you do your convolution, throw in a max pooling also. Do you guys remember your max pooling when we did CNN in part one? Guys, do you remember we did every convolution layer would have convolutional filters and pooling.
Yeah.
Yeah. So here you don't see pooling. You can add them up. So anyway, that's that.
They're in the vanilla encoder, or just using that as a function in a Jupyter notebook?
No, no, just do it here. You go modify it here. Or you can copy this code into another class, and then in that class you can go and put that. Or you can do it in Jupyter Notebook, whatever you feel comfortable with.
So max pooling layers in the build encoder.
Yeah, encoder decoder. See what happens. So this is that, and then when you do this, as we saw in that thing, now I tried to run my notebook, and I am in the same broken state as you guys are at this particular moment, but for what it is worth, let me open it here. So yeah, see, I managed to successfully reproduce the same mistake problem you guys were having. So now I know. And I'm pushing the effects in a little bit. So if you, and this also training the denoiser autoencoder. Anyway, we'll visualize the results, and the results were here still. I haven't removed it. So I'll have to make this fonts a little bit smaller for this page to be reasonably sized. Okay. And then when you go to the convolutionals, you see it, 16 channels become 32 channels, become 64 channels. You have a lot of channels, and you see the kernel size increasing, right? But when you use it, it is very much the same. You don't notice the difference at all, right? Except that the results are better. And then there's a denoising version of it. Add some 30% noise to it, and then you can run it. At this moment, it won't run because things are screwed up. So you guys have the results. That is it, guys. So how did I add the noise? Exactly the same way. Take the original image and add some extra noise to it. And that is autoencoders, guys. Now, remarkably, these autoencoders today are used for one set of purposes. They're fairly versatile. You can use it for many, many things. When we do anomaly detection, we'll again come back to autoencoders, and you'll see that we can use them quite a bit. And at some point, I wanted to introduce a lab dedicated to variational autoencoders, but then I realized that it's becoming a bit too much of autoencoders. I'll make that optional, and those of you who want to attend the lab can attend it later with me. So any feedback, guys? Are you finding this whole encoder decoder business simple?
Yes, I have a question.
Go
So,
ahead.
you did this for images. The
Yeah.
same thing can be done for text, isn't it? Or is there any reason you chose the images for this?
It works well, like image, it worked well. You can apply it to numbers, literally that. Any kind of numerical input itself, it will reconstruct, right? Any kind of feature vectors, you can feed it, and it will learn a lower dimensional representation of it. Image, the reason I gave image is because it's very visual, Shankar. People can see the effect that it has, managed to compress it and then recover from, decompress it, reconstruct it fairly efficiently. So because it was very visual, I used it this way. You can use it for any kind of feature vector. And that includes normal tabular data. It includes audio. It includes textual data, everything. Autoencoders are very, very versatile. So maybe maybe we need to do more examples. If you guys are interested, see guys, the question is we are moving fast. Already you guys need time to catch up. Uh, I can bring in examples. Would you guys want that? Examples of textual and tabular data autoencoding.
Some would be nice.
Yeah.
Okay, I'll bring those in. But we need to, the only thing is that where is the time for that? Because we have a limited number of sessions left. I will probably do an extra session for that. Shankar, would that be okay? Are you interested in that, Shankar?
No, I was thinking that we were all doing the spacey text, and then the next week, this week, it's going to be transformers.
That
So
is true. It was supposed to be transformers. Last week, I did this whole word embedding, and I motivated word embedding by saying this is part of the bottleneck methods. So that was also a good opportunity for me to take a digression into autoencoders. Otherwise, autoencoders would never have been covered in this deep learning workshop, right? I didn't get a chance to cover it in the foundations in part one, where it belongs. We didn't cover it, so I used this time to cover it. So now you understand, Shankar, right? You, yeah, because you weren't there in the part one, you wouldn't even know that we missed it.
but I was more focused on NLP related stuff. So maybe next week when you do the transformers, probably.
Yes, yes. So we'll get back to now. It is back to that. Not just next week. This week is the quiz that I'm releasing is on embeddings, word embeddings. Right? And from next week, it is all attention. In fact, almost everything going forward will be attention-based models, quite a bit.
So
Well,
can we do the examples on this Saturday noon after the quiz?
I'll try. How about that? I'll try, or I'll try to release it at least, give a few more examples. Huh? I'll try to take some tabular data. See, autoencoders can do even very basic things that you wouldn't have thought of. You just give it numbers and you try to just give it some numbers, whatever number sequences you have. And you ask it to reconstruct the numbers, it will do that. Soon it is producing numbers exactly the way you want it. It can learn all sorts of odd patterns in the data. So I'll do some feature tabular data and some for text data. I'll throw in examples from all of them.
Asif sir, can it be used for topic modeling as well, like finding the topic from text?
That's a very good question. Good that you asked. See, topic modeling is reducing to a lower dimension. Have we people tried to apply autoencoders towards that purpose? See, the problem is that the latent vector space can be thought of as topic. So there is some body of work. Um, it's not very common, but I'm sure there is some work. Huh? Let me find out, and I'll try to bring in an example of that. I do know people have tried.
Okay,
There is some data there.
thank you, sir.
As if is it is there going to be a lab on embedding?
Didn't
Like
we do the lab on embedding last week?
that,
Sorry, Shankar, go ahead. Guys, remind me, I'm forgetting what we did the previous time. Did we not do a lab on word embeddings?
There was theory for sure, but lab I do not remember. But I have skipped some lecture as well, like some classes.
Yeah, if
But
I have not done, then I better do it. So remind me, guys, is there a lab on it? See, embedding labs are very straightforward. It'll take, Shankar, it won't take too much time. There are two ways of doing embeddings. The pre-built embeddings, like, the glove and the
yeah,
word to the skipgram, word to vec and fast. Those are, there are only a few simple examples you can do
yeah,
because those things are done.
Yeah, we did a lab.
yeah,
Yeah, that was the previous lab,
yeah,
Sif.
yeah.
We have
So I
done.
was talking about the custom embedding.
Oh, custom
Next-
embedding we are coming to. That is with attention. No point in training, the traditional or the classic embedding
Okay.
I can do that, but it's not worth it. Times have changed, right? Why not do the state of the art?
Okay. Yeah. You covered embedding in the last one, the spacey,
Yeah.
using the spacey and gensim. Yeah.
Yeah, that's right. So then let's move on to the state of the art. See, you can train a custom embedding like your word to vec, etc., on your domain. It is of some value and sometimes it is useful. But nowadays we live, transformers have changed everything. Right? Let's do it with transformers, use custom embeddings and things like that. All
I
right.
see the question that Pradeep asked, that's intriguing me too, right? When each of these are different approaches, like the approach that we're looking at right now with the bottleneck method,
Yeah,
allowing some kind of a feature extraction, right?
right,
The whole concept of topic modeling also did that. Is it
right.
just that there were two different approaches and but essentially solving similar problems? Is that how you would summarize, or is there some nuance to it that's worth understanding?
See, there is a lot happening there. No? The autoencoding takes a very different, see, when you do topic modeling, how do you do it? Yes, for example, you can use autoencoders also for that, but you can do principal component analysis, you can do many things, or you can do latent Dirichlet allocation, you can do uh, you can do SVD, singular values and so forth, latent semantic analysis. All of those are to uncover topics, right? Autoencoders are a tool to solve a wide class of problem. When you use, for example, LDA for topic modeling, it's a particular algorithm to solve topic modeling problems. It works sometimes, it doesn't work. Yeah. Actually, I would go so far as to say that topic modeling, right, unfortunately, is in a pretty unsatisfactory state. We have made progress. It works sometimes, but quite often it doesn't work very well. The topics that come out are not very good, and so on and so forth. It
So,
is somehow useful, but yeah, you can say that, these are different pathways to get, like, for example, should you use autoencoders? Should you use SVDs? Should you use LDA? There's a no free lunch theorem that we taught in ML200. So would somebody like to rephrase what that no free lunch theorem was, guys?
There's no perfect algorithm for your data.
Yeah, another way to put it is there is no algorithm that will, in general, be better at other algorithms for a wide class of problems. For each problem, data favors some algorithm, and your task is to find which algorithm it is favoring, which approach it is favoring, and use that.
as if the way I was internalizing it right now for myself is the autoencoder, the concept that we're learning here is more like a means to an end,
Yes,
whereas topic
it's a
modeling would be an end in itself.
exactly. That's a very clear application. Autoencoders are a tool. They are a means to an end. Yes.
Okay, thank you.
But it's a very powerful thing, guys. Just as you have convolutional architecture, you have we did the transform attention architecture. We did a little bit of that. We covered the attention paper. We did RNNs. We did, the standard deep feed-forward networks. Now, autoencoders is a particular architecture that you can build out of pieces, underlying pieces like feed-forwards or CNNs, convolutions, or whatever it is, but it has a tremendous uh, or wide range of applications. I give this example of cleaning up image because to me that sounds, the first time you see it is quite remarkable, or you see an autoencoder fill in the blanks of an image. It is quite remarkable because it has learned from the data. It is filling in a gap based on what it has. In some sense, a trained autoencoder has memory of all that it has seen. It remembers how this image should look like, without the mask, and it sort of fills it in.
Asif sir, one observation. I was thinking that if we use autoencoder for um, topic modeling, the problem is that how how to find the topic, in the sense that whether it will be based on one word or a phrase or a combination of basically the the it might be very complex to find what is the meaningful topic.
That is true. Let's find out. Huh? I'll look at it. See, there must be, I have seen some chatter of autoencoders in this space, but I haven't pursued it. And I have obviously not written any code myself to do topic modeling with autoencoders. So I'll have to study it and come back with it. Find what people have done and come back with it. You guys are also welcome to contribute, guys. That's how we have a Slack channel. Search if anybody has successfully created good results with autoencoder for that topic. Somebody has found a clever way to use it.
Right.
All right, guys, we are hitting the time, 9:30. And was this lab useful? I hope.
Yes, it was.
I'll
Going
fix.
through the vanilla encoder code was useful,
Yes, yes,
and the other part
yeah.
be
And
better.
it's quite amazing, actually. Once you learn how to write an autoencoder, there's so many variations of it. If you go to our course webpage, let's go there. And I believe there's an entire section on autoencoder. Where is it? I can't. Autoencoder should be NLP topic modeling. We have so much of information now on the website. Practice. Okay, I am myself feeling a bit lost. Did I or did I not add a section on autoencoders? Oh, maybe I haven't. But I do have in my bookmarks a lot of very good resources on autoencoders. I'm going to add them. Huh? Let me search for the word autoencoder. Quiz on autoencoder. Content. Quiz. No, we don't have that. Okay, I'll add a section on autoencoder that is due. And you'll realize that there's a huge body of work that people have done in this space. See, each of these topics, right? There's so many researchers trying things out. Every single thing. So, guys, this weekend, our topic for Sunday will be how how transformers reconstruct the classical NLP pipeline. The spacey pipeline in which you first have you break up the word, you do the part of speech tagging, and so on and so forth. So it turns out that when you look closely at transformers, quite magically, they seem to have taken or learned about data in the same way, which is quite remarkable. It means that this whole approach that linguists used to take, breaking up word, computational linguists used to take, breaking up words, text into words, and then doing all of this tagging and this and that, was the right approach because this these transformers do the same thing. And another way to put it is it's also astonishing that whatever body of knowledge has existed in classical NLP, transformers have essentially rediscovered it in some sense. So that will be our paper for this Sunday. And the quiz will be on word embedding. On word embedding, we have not had a quiz. Is that right? I haven't given a quiz on word embeddings.
As of when you say the things they traditionally did, do you mean dependency graphs?
No, not the dependency graph. That is quite interesting. When the transformers learn from text, a document, it turns out that in trying to make sense of it, and knowing what pays attention to what, it does something very similar to your dependency graph. First, it does parts of speech. Then it finds, when you look at what is paying attention to what, you will see a very close resemblance to the classic dependency graphs and so forth. So wait till Sunday, we'll have fun.
For the week time, there's only one lab.
Prachi, I can't hear you.
For the week time, right? So only one lab has been uploaded. So the second day I could see only
Still very hard to hear. I heard week 1 and lab. It's a little hard.
okay. Can you hear now, Asif?
Now it is clear.
Yeah, see, for the week 10, right? So we had only one lab word embedding. So the second lab is not uploaded.
Yeah, this is the lab. That is the lab of today. I uploaded it.
Okay.
And it has a little bug in the vanilla encoder. I'll just fix it and post an update on Slack.
Okay.
And so this week, we will get into attention. All our labs, now we'll get intensely into a few labs to deal with transformers, and then we'll get into time series. Right.
And as if the paper that you suggested for Sunday, is that already uploaded to the portal?
No, I haven't. I was just looking at it. Let me see, paper. Hang on 1 second. Let me see if I have uploaded it or not. Yes, I'm a NLP. Oh no, NLP word embeddings. Yes. By the way, guys, before I continue, NLP word embeddings is there. All these resources and papers are there. So do please go and look at it. That's what I remember that I put it. Okay, now going back to your stuff, hands-on lab, suggested projects, weekly readings of research papers, weekly rethinking the attention, paper. No, I have not uploaded that. I'll upload it there. I'll put a link there for that paper.
Okay, thank you.
Anything else, guys? By the way, guys, if you go back and look at your textbook, the deep learning textbook, which I hope you are trying to read through, you'll realize that I've covered a large part of it. Is anyone following through with that textbook? The Ian Goodfellow textbook?
Read it.
Yeah, guys, do read the textbook. It's a good review of what I'm teaching you. And if you look at it, we have covered quite a bit of the book at this moment. The amount that is left is not that much. We'll cover the rest.
Asif, the question on the schedule, right? So so what do we plan to cover this, like this week, next week, week after, till we go to?
This week, I will review the attention. I will actually go deeper into the attention model. When I did it in the foundations, we gave 1 day to transformers. It didn't prove enough. People got overwhelmed.
So Asif, then for me, it will be even double problem, right? Because I didn't attend the first one. So how would I get?
Because I'm going to repeat it.
Okay.
So I'm repeating it this week. And then next week onwards, the labs will be on transformers, a couple of weeks, maybe a week or two. And I'll apply transformers to various NLP, natural language processing tasks, quite a few of them.
Okay.
And that will be a good segue after that. Image will have to be, we don't have that much time left. We have 5 weeks left. So we'll have to budget a little bit carefully. We will have to do 2 for, let's say, transformers and NLP, 2 more weeks of NLP. Then we'll do maybe 3. It depends upon how fast we go. And then 2 for time series. And somewhere in there, I'll squeeze anomalies.
So time series will come towards Christmas time.
Yes, of course. Why waste time over Christmas? Holidays are anyways, isn't it? Yeah, I'm kidding. No, yes, somewhere around that. Maybe New Year's we'll do the time series.
Okay.
And we'll cover everything else before that.
Okay, sounds good. Just trying to set myself to at least do something better out of this.
And guys, the reinforcement learning is in my mind. I will try to add some things later on. After this workshop is over, I'll put together something for reinforcement learning. So anyway, I'll close now, guys, but one request. Do make progress on your project. Guys, I asked you guys to create an open API doc. Have you created that? All I wanted is a API for your application. How many of you successfully did it?
Open API doc. Haven't. You had a resource for us to read about how to best do that?
Yes, we had an extra session for that. You remember?
No, sir. You just mentioned it, but we didn't have any session based on that.
Okay, so that is all the more reason we need to do some progress on the labs. Let me find time and give a session on how to craft APIs. There's a right way to craft APIs and there's a wrong way to do it. So I'll give a session on that. And along the way, see, the reason to me the project is important and to make progress is that's how you learn how to do an end-to-end deployment in the cloud. But in any case, I'll release the solution and document it. So if nothing else, if you don't get time, at least follow through with the solution and read the doc that comes with it. And if the vaccine comes out, we'll have a proper boot camp where you'll be there from morning till night.
And biryani.
And biryani, you remember that? Yes, nice biryani, and 12-hour sessions, 12, 14-hour sessions to do the projects. I can pretty much see that in the world of pandemic, it's hard to get the projects through. Okay, guys, I'll end now. I'll leave you guys with one puzzle as an exercise in collective intelligence. Predict the day we will all get vaccinated.
Never, because I'm not getting it.
What's that?
Never, because I'm not getting it.
Oh, goodness.
No, I'm getting it.
Well, it wouldn't make sense to be the first round, but eventually, when it makes sense.
Oh, yeah, we won't get it anyway. First, the essential healthcare workers will get it. Then the people in old people's homes will get it. So there'll be a prioritization. I'm told that by the time we get it, it'll be somewhere between September, October, November, December.
Yeah, that's my guess as well.
Yes.
Yeah, well into next year.
Yeah, the casualty of that is I'm not able to push you guys to do a lot of labs. Being there in support vectors, right? I think it creates its own atmosphere. Those of you who attended the boot camp probably agree, right? much more motivated to do labs than.
Right.
Srini?
Indeed, agree.
I can't believe that the whole facilities has just been closed now for almost a year, completely locked down. All right, guys, bye then.
Thank you, Sif. Good
Thank
night.
you.
Good night.
Thank you, Asif. I sent you, well, Cindy has outstanding stuff. Thank you.
Oh, okay. Yeah. Actually, could you stay back, Kate, for a moment?
Oh, sure.
All right, take care.
Okay.
Then as if
Patrick. Prachi, are you having fun so far? I think Prachi has also more or less left. So I will. Prachi, are you waiting for something? No. Okay. All right, Kate, it's just you
Yeah,
and me.
Patchy.
So bring me up to speed. I've seen a flurry of email from Cindy come up. I haven't fully dived into each of them. Could you give me a brief understanding of what has happened?
Okay. I think you understand how she has sent some emails clarifying how she wants to use the visual tokenizer to combine with the um, semantic information she has in her car's database to try to tie those together in a novel way. Uh,
Yes. That
so
is
she has
literally what I'm writing up. Yes.
yeah, so she has latest emails that just kind of clarify it, good pictures, and she has some budget question. I think for you to have an updated estimate of computing resource cost for her to put in the budget for her proposal.
Okay. All right. So let me get to it right away. I have a meeting with India, perhaps till midnight, and then I'll.
Your 10:30, yeah.
Yes. I'll get to it. Oh, you remember the times.
Yeah.
Kate, so far, how are you liking this workshop?
Um, it's good. I think it helps that I've done some previous rounds and I've had a chance to read more of the textbook because there can feel quite a scattering between there's of course so much stuff to study between the different libraries and the theory of how the algorithms work and um, the Python details and just sometimes you're like, what should I read first?
That's right. No, it is indeed. This is a pretty intense course. I mean, the unstated thing is you shouldn't be doing anything else if you want to really, really get something out of this workshop.
Yeah.
Otherwise, you fall behind. Like people like Shridi, etc., who are doing it along with a full-time, stressful job. I can see how it's very, very easy to fall behind.
Yeah, and even those without a full-time stressful job, there's just kind of only so fast your brain will absorb and retain it. It needs a certain amount for the information to start sinking in,
That's true.
so it's not all
Yeah.
overwhelming.
Yeah. Are you
So,
available?
I'm getting there. I would have liked for things to be faster, but I still feel like I'm making progress and I think I'll be able to, I like the eloquent transformer project.
Yes.
That's
No,
a
no.
good thing. Um, oh, yeah, we should probably start recording.
Oh, yes, yes, yes. Actually, I'll have him. That's a good point. I'll have him, uh, the videographer, remove the last part of the lecture
Yeah,
recordings.
that's okay. Perfect. I don't think there was anything that detailed that was revealed anyway. Um, yeah, so it's coming along. Like you said, it's a journey, and I'm getting there. The mountain is just taller than I thought.